Hello and welcome to Ready to Derive. As mentioned in the last video on limit laws, the only tried and true way to determine limits is to use algebraic methods rather than relying on graphs and tables. In this video, we will explore the most common methods: factoring, simplifying complex fractions, and then factoring, and rationalizing. We will also look at the case of an absolute value function, where it is first necessary to express it as a piecewise function in order to properly simplify and analyze. Without further ado, let's get started. So the first method in terms of solving limits algebraically is always try direct substitution. So if you can actually plug the value of x into the function and not get an error, then go right ahead. That means that the function is continuous right there. So let's take some examples. So from the previous video, we would technically think of using the limit laws here, where we would separate the limit up. We have the limit of a difference of two functions, so we could do the difference of the limits, and we see this constant 3. We could even put that 3 in front, bring that out of the limit, extract that as such, and then at that point we can just plug in. So the limit of x squared as x goes to -2, that's legal, minus 3 times the limit of x as x goes to -2, just plug in -2. We get 4 plus 6 is 10. Now, in future, though, you actually don't have to break it apart using the limit laws. Once we, know that it's a function that gives legal limits, we could have just plugged in x equals -2 right into the original problem, the original function, and got the same answer of 10. So what about the limit of cosine x as x goes to pi? Well, let's try it. Cosine of pi, can we plug that in there? Yes, cosine of pi exists, it's -1. So what about a situation where we run into a problem? Let's see what happens here. So when we plug in, if we try to plug in 1, we get 1 squared minus 1 over 1 minus 1. This should look familiar. 0 over 0, and the answer is said to be indeterminate. Now, what indeterminate means is that it's not clear what the answer is. So, for example, we know that 6 divided by 2 is 3, because we can confirm that with 6 being 3 times 2. But what is 0 over 0 equal to? Is it equal to 3 also? Well, let's check. 0 equals 3 times 0. Well, that kind of works. But then could we not also put 0 over 0 equal to 1,000? Because is not 0 equal to 1,000 times 0? So given that the answer is not clear, that is why this situation is referred to as indeterminate. And now we need to learn some new methods to deal with that. So the limit we were just looking at, which resulted in indeterminate form, should look familiar. From previous videos, if you recall, it was the straight line with a hole in it. And here's the corresponding table that we were using. So to solve a problem like this, what we have to do is just a little bit of algebraic manipulation. As we notice, the whole problem with plugging in x equals 1 is that x minus 1 in the denominator would give 0 in the numerator 0 as well, but it just appears that x minus 1 is a problematic factor. And factor is the key word here, because if you notice, the numerator can be factored as x plus 1 times x minus 1. And then we have that x minus 1 in the denominator, and at this point, x minus 1 cancels out at the top and the bottom, and we are left with a situation where it has become legal to plug in the value of x, i.e. use direct substitution. So we plug in 1 plus 1, we get the answer of 2, and we can confirm that once again from the graph. So at x equals 1, we have determined there is a hole at y equals 2. At x equals 1, here we would not know what the value of y is at that hole, but we could see from the table that it seemed to be approaching 2. So When substituting the value of x results in indeterminate form, try simplifying, and this is one method of simplifying, is using factoring. So let's try one more example of factoring before approaching different types of functions. So if you were to plug in -2 into the numerator and the denominator, you would get 0 over 0, indeterminate form. So we know that we have to look for an alternate way. So if we factor the top, we get this. And if we factor the denominator, we get x plus 2 times x minus 1. And so the x plus 2's cancel. Well, that is convenient because if we want x to equal -2, then x plus 2 was the problematic factor. So we get left with x minus 2 over x minus 1. Now let's just check. Can we plug -2 in by direct substitution? We would get -2 minus 2 over -2 minus 1, which equals -4 over -3. The answer is 4/3. Now we're going to embark on a sort of different types of functions that require different techniques. So let's look at this one that involves complex fractions. Again, if you plug -5 in, you would find that you got 0 over 0. So let's engage in some algebraic manipulation. We have complex fractions. We learned in Algebra 2 trig that we can reduce them to more simple fractions by getting common denominators and dividing, etc. So the common denominator here would be 5x, and we would have 5 plus x in the numerator. And let's see if anything good comes of this. So then we have 5 plus x over 5x divided by x plus 5, which you can think of that as x plus 5 over 1. So notice that I keep bringing down the limit statement. Don't lose this limit statement until the last step when you use direct substitution. So this is the same as times 1 over x plus 5. And look right there, we have 5 plus x in the numerator, a factor of 5 plus x, and x plus 5 in the denominator. They cancel, and we are left with a situation where we can plug in -5. So at this point only do I remove the limit statement as I legally plug in the value of x. So we get 1 over -25, and that is our answer. So you'll note that the problems are sort of contrived in a way that they work out nicely most often, but we will come across a situation where we're moving merrily along and we find that we kind of reach the dead end. So here is a problem where factoring wouldn't work. We can't really factor that numerator, and we haven't got a complex fraction. So we have to use a technique here called rationalizing, which you will have probably used before, but let's review. So again, plug in x equals 3, you will find that the numerator and the denominator both work out to be 0. Indeterminate form, let's use an algebraic technique. So rationalizing involves multiplying the top and bottom by the conjugate of the radical expression. And the conjugate is where you rewrite the radical expression, but you have, instead of minus, plus, and vice versa. But whatever we do to the numerator, we have to do to the denominator. So get this. And at this stage, you will FOIL the numerator. The nice thing about multiplying the conjugate is when you FOIL, you do the first terms. The radical x plus 1 times radical x plus 1 is just x plus 1. And the outer and inner terms will actually cancel because of the plus and minus. That's what's great about a conjugate. So you only then have to do the last term, so the minus 2 times 2, which is minus 4. Now for the denominator, don't FOIL, just leave as is, and you will see why. So x plus 1 plus 2. And then we get the limit as x goes to 3. Let's just simplify that numerator. How convenient. It becomes x minus 3. And we see that very shortly we are going to be able to cancel that out. So x minus 3 over x minus 3. So we get the limit as x goes to 3 of 1 over square root of x plus 1 plus 2. At which point we can use direct substitution. So I lose the limit notation and I plug in 3 plus 1 plus 2. And I get 1 over 2 plus 2, which is 1 over 4. So when you see a radical, be prepared to multiply the top and bottom of the expression by its conjugate. Now recall we said always try direct substitution first. Well, the problem here is if you plug infinity in for x, you get infinity over infinity, which is another type of indeterminate form. We actually I approached this problem in a previous video more intuitively, but here we're going to learn an algebraic method to simplify this. So the technique here is to, wherever possible, ensure there's no x's in the numerator of each expression. And the best way to do that, because the highest power is x cubed, would be to multiply the top and bottom by 1 over x cubed. And let's see what that results in. So in the numerator, we would get 4 plus 2 over x squared minus 5 over x cubed. And in the denominator, 6 minus 3 over x plus 4 over x squared. And why is this more useful? Well, the one thing that you should know, and we've looked at this type of situation before, is that the limit of 1 over x, as x goes to infinity, we know that a horizontal asymptote exists. 1 over a very large number is going to get close to 0. And that is true if it's 1 over x, or 1 over x squared, or 1 over x cubed. Any power of x in the denominator, 1 over that, the limit will be 0. So that allows us to, in a way, substitute. It's not really substituting, it's just acknowledging end behavior. So that if we think about it, sometimes we write it like this. This is going to go to 0. Let me use a different color. This expression as x goes to infinity is heading to 0. This and this. And we are left with an answer of 4 over 6, or 2/3. And this method works even if the degree of the numerator is different from the degree of the denominator. So if you had something like 4x squared as the first expression over 6x cubed plus ... You can do the same thing, but just do 1 over the x to the highest degree that you see in the function. So as I mentioned before, sometimes these limit problems seem very contrived because they always work out to a nice answer. So let's take one where we have to do a little more thinking to get the answer. If you plugged in x equals 2 to the beginning, you would have got 0 over 0. You can just assume that because that's why I chose the problem. So we go to the next available method, which here would be factoring. And perhaps we even get a little excited because the x minus 2's cancel. And so we have this. But we have not removed the problem. If we plug x equals 2 into that, we get 0 on the denominator. And your inclination might be to say, well, that limit doesn't exist, which it is true in a manner of speaking. But remember, we really have to, could be that the answer is infinity. So let's try looking at the limit from the left and the right, just to be sure. So if we recall, if we do the limit from the left of 2, like 1.99, this is going to tend to 0 in a negative sense, and 1 divided by 0 in a negative sense, we think of as negative infinity. If instead we come from the right of 2, that would be like 2.001. This will be heading closer and closer to 0 from the positive direction, which in fact is positive infinity. And since those limits don't match, then it is true that in this case, the limit does not exist. So there's one more case we have to consider how to handle the limit of an absolute value function. And what's most helpful here is to be able to rewrite the absolute value as a piecewise function. So to help us do that, let's just look at the numerator, the absolute value part, and it also might help to think visually. This isn't necessary, but it helps visually to think that the absolute value is a V-shaped graph that has been shifted over 2 to the right. And why this is helpful is then it's clear that it's composed of 2 piecewise linear functions. So let's think about what the equation of each of these functions are. So if we look at this branch here, this is where x is greater than 2. And if x is greater than 2, then the quantity in the absolute value function is positive, or will be positive for any x value greater than 2. So we don't really even need the absolute value there. This will automatically be positive. And that would be the equation of this branch. On the other hand, when x is less than 2, x minus 2, that quantity will be negative. We put the absolute value around to become positive. So the quantity x minus 2 will be negative. The only way to make it positive without the absolute value sign is to put a negative on the outside. So that is the equation of this branch. So let's take a look at the function then in the 2 scenarios. When x is greater than 2, we don't need the absolute value, and it turns out that that ratio is just 1. And when x is less than 2, let's replace the numerator with this expression, and then we realize that that will equal -1. So now if we re-examine the limit from each direction, so let's break that limit up into the limit as x approaches 2 from the left of this quantity. And that's this case, when x is less than 2. So we know that limit will be -1. The limit from the right, which is we're looking at this expression, will turn out to be +1. And because the limits from the left and the right do not match, we know that this limit does not exist. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.